Any general questions, problems, anything? Then the only real announcement I have, again, I did send an email yesterday, is the first homework, OWL homework, is due tomorrow, technically. But again, they stay open, so if you have questions or something that pop up later, or you don't have time, or something's unfamiliar, it does not matter one bit if you are a day late or something. Okay, so just sort of wrapping up these types of forces. Again, if you, in order of strength, and again, this assumes equal distance between the two different molecules, because all of these forces vary with distance. So, you know, it's an apples to apples comparison. Ionic forces are by far the biggest. Technically, the second largest is a hydrogen bond, because that's an extreme case of the dipole-dipole, which weighs in at number 3. And then the weakest in general is the van der Waals force. But, right, the bigger the molecule, the bigger the van der Waals force. Right, and so for really large molecules, the van der Waals force easily moves up to number 2 on the list, which is why I usually consider the van der Waals to be the second most in terms of importance, right? If I've got a polar molecule that either has a dipole-dipole or hydrogen bond, I might move it up because of that, but I would first assess the van der Waals forces, because that's really just the size issue. And for a giant molecule that happens to have one OH bond, as we saw on Friday, right, the effect on the boiling point is muted. It's not that it has no effect, but it's only strong in the area of that one single bond, whereas the van der Waals force is the entire molecule. So, right. The one thing I'm always 100% confident in saying, however, is the ionic forces are biggest by a lot. And so if you have an ionic compound, right, because of the nature of the ions, they're all clumped together and they're virtually all bonded to all of their neighbors, right? They are by far the biggest. Okay, and again, we were using melting point and boiling point as sort of an indirect way of assessing the strength of them, because as we were talking, right, phase is really the interplay between the intermolecular forces, which are trying to hold them together, and the temperature, the kinetic energy, which is trying to get the molecule to keep moving, right? And so the higher the boiling point, the stronger the intermolecular forces. It's indirect, right? But it does give us a way to sort of quantify the relative intermolecular forces. It's worth pointing out that there are other properties that depend on intermolecular forces. Because again, the intermolecular forces are just a certain molecular stickiness, right? So they affect other things like viscosity, which is pourability, right? Honey is more viscous than water, right? It doesn't pour well, right? And the reason is because the molecules are sticking together more, right? Capillary action, you know, you've seen this with straws. This is the tendency of the liquid to crawl up the straw, right? That is, again, an intermolecular force between the liquid and the surface, inner surface of the straw, right? And so there are other forces that manifested, but for the most part, because it's more familiar and because it allows us to do other things, we're interested in the phase side of things, right? And so really, we tend to think of phase changes in terms of the temperature, and that's the hand wave that I've been doing, but that actually assumes that the pressure is constant. because there's really two things that are affecting the molecules, right? The energy directly is the molecules moving, but there's also what I've termed the space issue or the confinement issue, right? If you squeeze the two molecules closer together, right, they have to feel each other, right? I mean, put two people in the closet, it's hard for them to ignore each other, right? You got to be really mad at the person in the closet to ignore them if you're locked in a closet. And that's the confinement issue. And that's really a pressure issue. We talked about pressure in terms of gases. And frankly, that's because pressure really tends to only be significant if there's a gas involved, because it's really hard to squeeze a solid and push the molecules closer together. It's almost as hard to squeeze a liquid and push the molecules together, right? But gases are highly compressible, and so that pushing does actually compress the molecules and confine their space, right? By definition, it's force per unit area, right? And so, you know, depends on which sign you want to use. Pressure, as it's normally defined, is the molecules bumping against the walls of the container. On the other hand, you can also push in the walls of the container, and it's now the container pushing on the molecules. And technically, you can create phase changes both ways, right? By changing the temperature, you slow the molecules down, and so they start to clump together because they no longer have the energy to escape each other. You can also, as you'll shortly see, do it with pressure, although again, it's really only effective if there's a gas involved, right? And so most materials have three phases, right? And you can transition between the three phases either by changing the pressure or the temperature or both. We're just mostly familiar with the temperature issue because we mostly do everything at the same pressure, right? Unless I build a chamber to confine my sample, if I'm doing it in the room, right, it's almost always about 1 atmosphere of pressure, unless you live in Denver. I know we have a couple Colorado people. I don't know if they're in Denver, but right. If you live near sea level, you spend your whole life pretty much at 1 atmosphere. And so we're far more familiar with phase changes mitigated by temperature because that's what we see. There was frozen water on the walk on my way here today, right? That is not because the pressure is different than it was in the summer, it's because the temperature is different, right? And so if I have steam and I start cooling it down, right, my steam eventually becomes a liquid, right? And where does it do that? It does that at the quote unquote phase transition temperature, the boiling point, which we usually think of as 100 degrees C, but this again is actually assuming something about the pressure that's usually true but doesn't need to be, right? 100 degrees C is not technically the boiling point of water because water will boil at any number of temperatures, right? 100 degrees C is what is termed the quote unquote normal boiling point of water, where normal actually means at 1 atmosphere of pressure. As we'll see probably Wednesday, if you live in Denver, Colorado, your water does not boil at 100 degrees C, right? And so you can actually change the pressure, which changes the temperature. And so really both need to be considered, right? You've got in phase the interplay of 3 properties. The intermolecular forces are always attractive and always trying to pull the molecules together. The kinetic energy, right, is always trying to pull the molecules apart. They want to keep moving because they have kinetic energy. And pressure, right, is a way of squeezing the molecules together also, right? And so if I'm trying to determine the phase, It's really a question of what the intermolecular forces are relative to the kinetic energy that's trying to push them apart, with an assist possibly from the pressure, which is trying to push them together and therefore help the intermolecular forces, right? And so really all three things matter. And so if I really want to talk about phase, I need to talk about pressure and temperature. The intermolecular forces are completely untunable, right? If you're two water molecules, you always like each other exactly the same amount. What changes, or what you can change, is the temperature or the pressure, which makes that attraction matter more or less. Right? And so, again, we tend to think of phase as strictly a temperature phenomenon, but it's really a pressure temperature phenomenon. And so the more complete way to discuss phase is in terms of what's known as a phase diagram, which is a pressure temperature graph for a material. Right. And unsurprisingly, right, there's three regions in my phase diagram. There's the pressure temperature combinations where I'm solid, there's the pressure temperature combinations where I'm liquid, and there's the pressure temperature combinations where I'm a gas. And if you think about it, right, these regions are not that surprising, right, if you consider what I was just saying about pressure, temperature, and intermolecular forces, right? Out on the right-hand side here, right, I've got high temperature, right, which wants the molecules to fly apart, right? So the higher the temperature, the more likely the intermolecular forces don't matter, right? I'm also down here at low pressure, which means I'm not squeezing the molecules together, right? Which also means the intermolecular forces matter less. And so no surprise, I am my freest at low pressure and high temperature because the intermolecular forces become virtually irrelevant. I got a lot of energy. Intermolecular force is always constant. I got a lot of energy and there's no pressure squeezing me together, and so I don't feel the intermolecular forces so much, right? On the other hand, if I go to low temperatures and high pressures, right, the low temperature means the molecules are moving slowly. Again, they always like each other the same amount. If you slow them down, right, that attraction matters more because they don't have the energy to escape it. And if you increase the pressure, you're squeezing them together, which also makes the intermolecular forces matter more. So at low temperatures and high pressures, I tend to be a solid, right? Liquids are sort of that middle region, right? I'm not really, really cold, and I'm not really, really squeezing them, right? And so I don't get the maximum out of the intermolecular forces, which would be a solid, and I don't get the minimum, which would be a gas. And so I'm in that middle region where liquids really do have, if you think about it, some properties of solids and some properties of gases. They're mostly like gases because they're fluid and the molecules move around, whereas they don't for solids. But liquids are also, for example, not compressible very much, like solids are not compressible, right? And so liquid is sort of a middle phase between being totally free and being totally trapped. Okay. And in my phase diagram, those lines are boundaries between the phases, right? And if I look at 1 atmosphere of pressure, those are what I tend to think of as the normal boiling points and melting points for a material, right? Because I tend to live my life at 1 atmosphere of pressure, and so I'm just moving along the x-axis, and I very rarely deviate much from the y-axis. And so this is the phase diagram for carbon dioxide. As you may or may not know, carbon dioxide, which is dry ice, sublimes at room pressure. So you buy the ice, it's chunks, right? But it doesn't actually go through a liquid phase. It just sublimes at room temperature and turns into a gas. And that temperature, again, the normal sublimation temperature is minus 78 degrees C. There's no liquid carbon dioxide at room pressure. If you want liquid carbon dioxide, you have to increase the pressure. Right, and so, right, water, which you're more familiar with, has all three phases possible at room pressure. So again, if I'm walking along the x-axis at the 1 atmosphere mark, right, if I'm below the normal freezing point, which is 0, I'm a solid. If I'm above the normal boiling point, 100 degrees C, I'm a gas, right? And in between, I'm a liquid. And so our experience of phase change is usually walking along that dotted line. All right. And so those three lines, ignore that little twist at the end of the bottom line. It's just an artifact of my less than brilliant Microsoft PowerPoint drawing, right? All three of those phase transition lines meet at a single point, which is called the triple point. In some ways, this is a useless point, right? You have to be at a very specific pressure and a very specific temperature. You don't have a lot of flexibility here, but it is kind of interesting, right? You can look at it as two different ways, and I will state it both ways, and you can decide which one you want to be shocked and amazed at, right? Either I've got solid, liquid, and gas coexisting together with no distinction, right? Or really, in some sense, the better way of phrasing that is, right, that if I'm at the triple point, I am neither solid nor liquid nor gas. Right? It's kind of an interesting point in space, in pressure, temperature, space. But as I say, it's not like there's a lot I can do with it. I mean, if I wanted to do some funky phase experiments where I was not a solid, a liquid, or a gas, I could dial in my triple point, but you know, it's a single point in space. Right. Of more use, right, are my transition lines, because they tell me what the boiling point and the melting point is when I change the pressure. The other point worth mentioning is this endpoint, right? I technically didn't get tired of drawing. That line really ends, right? As does this other line, the liquid solid line, at some point, because if I'm above that temperature, I have so much kinetic energy that the intermolecular forces are incapable of holding me together no matter what the pressure is, right? And so technically my phase diagram sort of ends at that point, right? Everything from here over, whoops, missed the point, but everything from here over is a gas, because I have just so much kinetic energy. Right. Boiling, to distinguish it from evaporation, I remind you, has a very specific definition. Boiling is the point at which vapor pressure equals atmospheric pressure. Right. And you might ask, that's great, you've just defined boiling in terms of vapor pressure, but you haven't defined vapor pressure, so okay. Vapor pressure is the pressure exerted by the gaseous phase of the liquid. if you were to look at a beaker of some liquid, right, above the surface of the liquid, there is some evaporated liquid. This is what I mean by vapor, right? If you think back to the ideal gas law and the issue of partial pressures, right? If I'm open, my flask is open, the total pressure should be equal to the atmospheric pressure. But I really have two components there. There's the air and there's the evaporated liquid, right? So that piece of the total pressure in the flask that is due not to the air, but to the evaporated liquid is what I mean by vapor pressure, right? And this is really the product of what temperature is, right? If you've got a temperature of your liquid, it doesn't mean all the molecules are at the same kinetic energy, right? The temperature refers to the median kinetic energy of the system, because the molecules aren't all swimming together in perfect synchronicity, right? Even if they start swimming together in perfect synchronicity, they bump into each other. And when they bump into each other, frequently energy is transferred, so somebody gets faster and somebody gets slower, right? And so in any ensemble of molecules, there's actually a distribution of kinetic energies, right? And so in that distribution, somewhere up here, there are molecules that are relatively hot, right? Which in this case, I mean they have enough kinetic energy to escape the intermolecular forces and become vapor. Right? Evaporation is still an intermolecular force issue, but now it's a very specific issue that's not tied to the temperature of the entire system, but essentially the kinetic energy of the individual molecules. Right? And so if I raise the temperature, all I'm really doing is moving the distribution, which gives me more hot molecules. And so boiling, right, is really a measure of how many molecules have enough energy to get into the vapor phase, right? And so if I raise the temperature, I'm going to increase the vapor, represented here by green squares, right? The total pressure for an open beaker should always be the same. It's the atmospheric pressure. And so what happens as I increase the temperature, I start pushing out. Well, actually, I had it backwards. The green squares were air. The blue, of course, is the liquid, right? I start pushing out the air because eventually the maximum vapor pressure I could have is atmospheric pressure, because the total pressure in the room should not be changing, right? And so if you need another reason not to stick your face over a pan of boiling water, this is it. You will suffocate, because there's no air by definition above the surface of a boiling liquid. It is 100% steam. If it's not 100% steam, it's actually not technically boiling, because by definition, vapor pressure has to equal the atmospheric pressure at the boiling point. And so all I've really done again is move my distribution far enough to the right by increasing the temperature so that I have enough molecules with enough energy to get into the vapor phase and force out all of the liquid, or excuse me, all of the air. Right. Right. And so again, if I'm not doing anything with pressure, it's fundamentally a temperature phenomenon. And solid to liquid transitions are mostly temperature phenomenon if you look at my phase diagram. Right. But my liquid to gas transitions are actually far more pressure sensitive right? And you can see that in the phase diagram, right, in the slope of these lines, right? If you notice, this is not an accident. In both of my phase diagrams, the solid liquid transition line is virtually vertical, right? It's a little off vertical. And if you look at carbon dioxide relative to water, right, carbon dioxide tilts a little bit to the right, water tilts a little bit to the left, right? But it's mostly vertical. And so it's very, very hard to make a solid liquid transition by changing the pressure because the pressure doesn't matter much, right? If I'm changing pressure, I'm traveling along this vertical line. If I happen to be right here, right, I can get to right here with pressure, but there's a very narrow temperature range where pressure is going to do me any good, right? On the other hand, if you look at the other two transition lines, solid to gas and liquid to gas, they are far more horizontal, right? And it's really because of the presence of the gas. The gases are compressible. They feel the pressure. And so, you know, I'm very, very flat in the sublimation curve because the difference between being a gas and a solid is the most extreme. And so pressure really matters, right? It's a little less horizontal for liquids or gases, but again, it's far off of the vertical. And so I can make a liquid to gas transition much more easily with a pressure change. Right. Although for the most part, again, we're still prone to want to do it more with temperature than pressure, because again, I'm usually in a beaker or something in a room where the pressure doesn't deviate very much, right? And so, you know, the always questionable metaphor I use, right? If I tie myself to one of you with a noodle, literally I'm talking, you know, cooked egg noodle, or if you want, uncooked egg noodle, right? Could you escape, right? There's always some smart aleck who says no. And I suppose if you spend enough time sitting in your room gaming, it's possible that you could not break a noodle, right? But if you just start walking away from me, I'm pretty sure the noodle's going to break, right? On the other hand, if I tie myself to you with thread, you're going to have to tug a little harder, right? And that's the temperature issue relative to the intermolecular forces. You can't do anything about the intermolecular forces, but as we've seen, some molecules, right, have stronger forces than others. So they're tied together with a noodle or a thread, you know, or in the case of ionic compounds, right, maybe wire or handcuffs, where you really have to be running fast to break the handcuffs, right? I bring that up because that is really part of my phase change process, right? This is not magic where I just get to 100 degrees C and everything goes poof, right, and boils, right? If I'm water and I'm at atmospheric pressure, right, I need to get to 100 degrees C to boil, but I still need to break the thread, right? And so phase changes actually involve two very different things, right? There's the kinetic energy issue, which is temperature. But even if I have enough kinetic energy, I am still tied. And so there's also the breaking of that tie, the severing of the intermolecular forces, right? And so if I want to, and sure, why not, take ice and start heating it up, right, I'm going to get multiple things happening. The first thing that happens is it just gets warmer, right? We actually talked about this in fall, right? If you add heat to a system, the temperature changes. How much it changes depends on mass and specific heat, right? But even when I get to 0 degrees C, I'm hot enough to be a liquid now, but I am still tied together, right? And so this sometimes also shocks and amazes people. You can have a 0 degree solid. You can also have a 0 degree liquid, right? Both phases are possible at 0 degrees, right? And so I don't just magically melt at the melting point. I have to actually cut the chains that bind, sever the noodle or the thread or the wire, depending on how strong the intermolecular forces are, right? To free the molecules enough to move. That is a very different process than just heating it, right? Because there is technically no change in kinetic energy here, right? Both of these systems are at 0 degrees C, right? Whereas when I'm minus 40 degrees as a solid or 0 degrees as a solid, there is a kinetic energy difference because that's what temperature is, right? And so those are two fundamentally different processes. These are usually represented by what are known as either enthalpies of the phase change or often heat of the phase change. Again, sort of a callback to fall, hopefully, right? Delta H is the enthalpy change, right? It's really just an energy change under very specific conditions. And so if I'm going from solid to liquid, there's energy I need to put in that essentially does nothing other than sever the intermolecular forces. There is no change in temperature. There's just a change in freedom, right? Similarly, if I'm going from liquid to gas, right? Liquids are relatively free, but again, to use my always questionable metaphor, liquids are essentially handshaking their way through life, right? If I'm going to be a gas, I have to free them from the handshakes, right? And so that is either called an enthalpy or heat of vaporization, usually abbreviated as delta H. And of course, if I go from solid to gas, if I sublime, I have to cut the chains all at once. And so there's a heat of sublimation. Typically for a given set of conditions, by the way, right? The heat of sublimation is usually, again, at the same conditions, so same temperature and pressure, is usually just the sum of the delta H of fusion and the delta H of vaporization. It is literally the amount of energy you have to put in to cut the chains. And so whether you partially cut them, stretch them, and going from solid to liquid before I completely break them and going from liquid to gas, or I completely break them, it should be the same total amount of energy. Right? And my superscript 0, which is what that little degree sign looking thing is, means standard temperature and pressure, which again usually means 1 atmosphere, and typically room temperature, 25 degrees C, right? But so if I'm going to go from solid to liquid to gas for something like water, I actually have to do, well, either 5 different things or 3 different flavors of 2 different things, right? Meaning I'm going to start somewhere in my pressure temperature curve. If I do it at atmospheric conditions, I'm probably along this 1 atmosphere line, but I start at some temperature, right? If I'm heating it up, right, to get to the phase transition line, I'm changing the temperature, so I'm adding kinetic energy, right? To cross that line is my enthalpy, right? So once I'm here, I have to stretch, elasticize, right? My intermolecular force bonds, I shouldn't really use the term bonds there, otherwise it sounds more chemical, but my intermolecular force bands, right, to free my molecules into the liquid phase. This is an energy term, but it's not an energy term associated with any kinetic energy, right? Once I've liquefied my solid, if I keep adding energy, I'm going to start changing temperature again until I get to my phase transition temperature to go from liquid to gas, where again now I have to finish cutting the intermolecular force bands, which is now a delta H of vaporization. And then once I'm past there, I can just keep adding energy and it stays a gas forever, or at least until I add so much energy that I start stripping electrons off and breaking down the molecular structure or something. As I often say, you know, if I do this on the surface of the sun, strange things start to happen. But under normal temperatures, right, my gas just gets hotter and hotter. All right. And so those are technically 5 different energy issues, right? There's a kinetic energy change for a solid, which is actually different, at least a little bit, than the kinetic energy change for a liquid, which is different than the kinetic energy change for a gas. And then there's those 2 different enthalpies of the phase changes, which are just energy used to cut bonds. And so if I want to look at this entire process, I really do have 5 distinctly different steps in the process, right? And so if I were to plot here heat added versus temperature, right, you can see my 5 different areas, right? I've got 3 regions where the temperature is actually changing, right? That corresponds to my movement between phase transition lines. When I'm at the phase transition lines, it's a delta H issue, right? It's a phase transition. And so there's energy involved, which is why the heat added changes, but there's no change in temperature because all of the energy I put in there goes into breaking the bonds, or excuse me, breaking the intermolecular force bands. Right. And so in terms of my water, I started as a solid. It becomes a hotter solid. Then it undergoes a gradual, because again, it's not magic, solid to liquid transition. As I add more energy, I melt a little bit more ice, a little bit more ice, and a little bit more ice. Once I'm completely liquefied, if I keep adding energy, my liquid starts to get hotter again until it gets to that phase transition temperature, right? At which point now I need to break what's left of those intermolecular forces, and so it's a delta H issue. As I gradually boil my liquid into a gas, and then once I'm a gas, onwards and upwards, any more kinetic energy simply changes the temperature, right? So this, on the temperature graph, right, corresponds to melting point, and this on the temperature axis corresponds to the boiling point, right? And so my separation between those different regions is dictated strictly by the phase transition temperatures. If I'm at 1 atmosphere, it's the normal boiling point, right, and the normal melting point. If I'm somewhere else, right, there's still, whoops, went too far, right, there's still phase transition temperatures, they're just not at the same point, right? And as you can notice, as we mentioned, a pressure change makes a much bigger difference to the boiling point than it does to the melting point, because again, as soon as there's a gas involved, right, it's more sensitive to pressure, right? And so I can make that journey at any pressure I want. It'll simply change what the melting point and the boiling point are on the axes. Right. If I drop the pressure all the way to where it sublimes, then I'm going to be down to 3 regions, right? There's going to be a solid heating up, followed by a sublimation delta H, followed by it's a gas, gas, gas for the rest of the journey. Right. And of course, I can do it the other way. If I start sucking energy out, I'm just traveling left along my phase diagram instead of to the right. Right. And we actually know how to calculate these things, at least some of them, right? If I'm actually changing the temperature, right, this is a Chem 1 throwback, right? The material response to a change in energy, call it heat, is for its temperature to change. How much depends on the amount of the substance, the mass, and what the substance is, the specific heat. Right? And all of my sloped lines there represent some MC delta T. The mass should be the same, of course, mass is conserved, but the specific heat of a gas is different than the specific heat of a liquid, which is different than the specific heat of a solid of the same substance. All right. And so those are really 3 different flavors of the same process, right? The phase transition energies, if you want to call this Q, you could. More frequently, it's an E for energy because it's not really heat, right? Is N, which is the number of moles, times the delta H, because delta H is usually normalized to the number of moles. Right? And so these are known for water in most common substances, right? Notice the specific heats of the steam, ice, and water are different. Notice, as I mentioned before, the sublimation temperature or sublimation energy is essentially the sum of the delta H of vaporization, the delta H of fusion. And if I want to actually calculate the amount of energy involved in that total process, I have to break down the journey into the 5 individual steps. Some of you are stubborn and will not want to. Some of you have been ruined by high school and basic testing theory. Because if I were to state this as a problem, and I will in a minute, right? I have a starting point and an ending point. And of course, basic theory says take those numbers and do something with them, right? But those numbers are really just signposts on a journey that involves a whole bunch of different steps. And I need to look at the 5 steps separately. There's no simple way to simply calculate the total amount of energy it takes to go from 500 Kelvin to 100 Kelvin if there's a phase change involved, right? Because every time the phase changes, the specific heat changes, right? And so I have to break up my journey into multiple steps. There's a fun animation here, but who cares, right? And so, right, if I were to start at 500 Kelvin on my way to, say, 100 Kelvin, I think was my endpoint, right? There's nothing necessarily in the statement of the problem that says go to 373 first. I know to go to 373 first because that is the boiling point, normal boiling point of water, right? And so really the position of those two horizontal lines is known to me not based necessarily on what I'm trying to do, but based on the material I'm trying to do with it. And so I go to 373 kelvins, not because I care to even be at 373 kelvins. My goal was to get down here at like 100 kelvins. But if I'm going to get all the way down here, right, my journey changes at this point. It's no longer cooling down a gas. It's now condensing, would be the technical term, liquefying a gas, right? And so I can only MC delta T until I get to a phase transition temperature. Right. And so MC delta T tells me, right, delta T, by the way, like all deltas in sciences, is always final minus initial. That's important just for consistency of the sign. Right. And so if I started with 50 grams of water at 500 kelvins, I need to remove, which is what the negative sign is telling me, 11,000 joules in order to get down to 373 kelvins. Once I'm there, I'm still a gas, but I can't become a colder gas because sucking out more energy will start to condense me, right? How much energy I need to suck out to condense me is given by the delta H of vaporization, which is written for going the other direction, which is why I put a minus sign in there, right? The delta H of vaporization is referring to the liquid to gas transition. If I'm going gas to liquid, right, same quantity of energy, opposite sign, right? And so if I want joules, I've got kilojoules per mole, right? I need to multiply it by moles. Right. I don't know, I wasn't going to mention that, but since it's there, the again, please note it's a delta T. So the difference in temperature in Celsius and kelvins is the same, right? If I subtract these, right, I get 127 kelvins, but that's a delta Kelvin basically. And so I don't convert that to Celsius. If I convert to Celsius before I subtract it, I get exactly the same amount. Right. More animation. Whoops. Right. As soon as I get to the 373, if I keep sucking energy out, it's going to start condensing. It's a moles issue now, not a grams issue, because of the units I had for delta H. And so 50 grams times 1 mole per 18.02 grams is the molar mass. Right, that gives me moles, times kilojoules per mole gives me kilojoules. So that's 112.9 thousand joules. Notice right? That's about 10 times the amount of energy it took me to cool that thing down, right? Generally speaking, right, this is the biggest energy step in any of these phase changes, right? If you think of it in terms of boiling, right, I need to completely free the liquid molecules from each other so they don't even know that there's other molecules around, right? That is the energetically hardest thing to do, right? If you look at the delta H of fusion, right, it's a factor of 6 or 7 smaller than the delta H of vaporization. That is almost always the hardest thing to do, right? Once I'm completely condensed, right, it becomes a MC delta T problem again. Only the specific heat is different now because I'm a liquid. Note the mass is the same because I'm still water, the same amount of water and mass is conserved. I just a different phase of water. And again, that works all the way down to 0 Celsius or 273 kelvins because that is the phase transition temperature at this pressure. And so I can stop anywhere along that line. If I want to be 50 degrees C water, I can stop here. There's no law that says I have to keep going until I get down there. All right. But if I want to keep going, again, everything changes when I get to the phase transition temperature because I can't simply keep changing the temperature at that point. I first have to change phase. Right, and then ultimately, I can then cool myself down to wherever I want to go with an MC delta T. And the total energy it takes, and I'll leave you there since we're over time already, is the sum of the 5 individual steps in the process. We'll look at another example on Wednesday, but again, I have to break it down into the 5 individual steps and treat each one separately. There's no way to take the starting point and the ending point and just use those to calculate it. There are 5 distinctly different physical processes and need to be treated as such. Questions or problems? Happy Monday. Enjoy the warming trend. By Thursday, we might break freezing.
Thank you.
Thank you, Professor.
Have a good day.
Thank you.
Thank you.